So let's do a quick review on what we know about net force. Before we get into the vertical part of it today, what do we know about net force? How can we solve for net force? Mass times acceleration, right? Net force is found using the equation mass times acceleration. That's one way to solve for net force. What's the other way to solve for net force? Do you remember? If I've got a free body diagram of an applied force and a frictional force, how can I go about solving for the net force? Right, I take the force that's pointing in the positive direction and I subtract out the forces that go in the negative direction, right? So the second way to find net force is to always take the positive force minus the negative force. And we need to reiterate that we're always going to do things in the horizontal direction separately from the vertical direction. Just like we did with projectiles, we're going to analyze vertical and horizontal motion separately. So if we're looking at a net force, we would never take the normal force minus the frictional force, right? We would never do that because one of them is vertical and one of them is horizontal, okay? So as we're digesting net force, we want to make sure that we're paying attention to only horizontal or only vertical, okay? Remember, what's this type of diagram called? A free body diagram, yes, a free body diagram. Good, okay? Where we draw all of our forces outward from our object. We draw them as arrows, right, as vectors, and we try to draw them proportionally to scale. Okay? So now let's talk a little bit about mass and what it means. Okay, mass is a quantity of matter. In our common everyday language, we use mass and weight. We use them in the same context, even though they really don't mean the same thing. Mass and weight, in physics terms, mean very different things. But in everyday life, we use those terms interchangeably, and really, they're not. I'm going to show you the difference between what those things mean. But mass is a quantity of matter. We kind of think of it as a measure of inertia of a body. Okay, the measure of inertia of a body. Okay, and so what that means is that the more mass something has, the harder it is for it to get it started or to slow it down. Right? If I have a heavy object and a light object, it's going to be much more difficult for me to change the motion of my heavy object. Okay, would you guys agree with that? I'll say it again here. If something is heavier, it's going to be much more difficult to change the motion of that heavy object rather than if something is light, right? If something's heavier, it's going to be harder to get it started or harder to make it stop. That has to do with the inertia. Do you remember what inertia means? Tendency to resist change. So if something's got a lot of mass, it means it has a lot of inertia, which means it really doesn't want to change what it's doing. Okay? All right. More matter an object has. Okay, we already talked about that. Kilogram is our unit for mass. Okay, kilogram is our unit for mass. That's what we would consider weight, right? If we say, how much do you weigh? We give the measure in kilograms. Well, that's not really a correct question. The question really should be, what is your mass? And give it in kilograms. Because weight, we'll see here, means something different. Okay, mass and weight are two very different things. Weight is a force. The actual term weight, it's a force. It's the force of gravity acting on the object. Okay, that's how things, it's a force. And what do we measure all forces in? What's our unit for forces? Do you remember? Newton. Our unit is Newton. So we don't step onto the scale and get our weight in newtons, right? Here we get our weight in pounds. You guys probably get your weight in kilograms. Okay, but when you step onto the scale, you get your mass in pounds, not in newtons. And so weight is technically a force. And like I said, in physics, those two things mean very different things. In real life, we use them interchangeably incorrectly. But, all right. That's why when you go to the moon, things weigh less. Okay, I know you don't have to write that down, but I want you to think about this. When I go to the moon, am I actually losing mass? No. I don't lose any mass from the time I leave on the rocket ship to get up to the moon. Yet I can float, right? I weigh less. If I were to sit on a scale on the moon, it would say I weigh significantly less. That's because the gravity on the moon is significantly less than on the Earth, right? Roughly a sixth of it. Okay? So I'm not losing mass, but my weight appears different because the force that's acting on me is significantly different. Okay? So the unit for weight is newtons. The unit for mass is kilograms. Make sure you write that down. That's a really big difference. And we're going to use that. We need to have that. Okay? When we look at the force for weight, we call it Fg, or the force due to gravity, or the gravitational force, right? Those mean the same thing. Fg, we can take Newton's second law, F equals ma, and apply it directly to gravity for the weight force. So instead of F net equals ma, now we have Fg equals m times g. Because isn't this g right here, it's just acceleration due to gravity, right? That's what that means. So what is the value of g? 9.8, right? The value for g is 9.8. And here's the thing, you don't have to put in the negative because we're always going to draw our gravitational force in the downward direction. And all the negative tells us is direction. So you don't have to put in the negative when we use it in to find the force. Okay? All right. Both the force and the acceleration are down. Let's try this. What's the weight of a 60 kilogram crate? So why our answer is not just 60 kilograms because 60 kilograms is the mass. So whenever we ask for weight, that means we're solving for Fg, right? The force due to gravity. So if I was going to solve for weight, I would say Fg equals mass times 9.8. Okay, mass times 9.8 gives us weight. And my calculator is here. So I'm going to take 60 times 9.8. And I get a weight of 588. What's my units for weight? Newtons. Good. Okay. There's a very big distinction between mass and weight. Your weight is almost 10 times what your mass is. So I don't really want anyone walking around telling people what my weight is. I don't want anyone telling me what my mass is anyway. But weight is 10 times greater than that. Okay. So those are two very different things. Weight is mass times 9.8, and it's going to be measured in newtons. Okay, does that make sense? All right. What happens if I say I have an object with a weight of, let's say an object weighs 45 newtons. How would I find the mass of that object? I just divide it by 9.8, right? I would say 45 newtons equals mass times 9.8. And I would divide over 9.8. And I would get, I don't know, 4.6. Does that make sense? So weight is just using gravity to give us that force. All right. Last law for Newton here is Newton's third. Okay, we went over his first. What was his first, Newton's first law? What was it? The law of inertia, right? Law of inertia. Things at rest tend to stay at rest. Things in motion tend to stay in motion. Second law was Newton's second law was force equals mass times acceleration. Okay? And the third law, this second bullet right here is really the catch line, or for Newton's third law. It says there is an equal and opposite reaction for every force, or for everything that happens, there is something that's equal and opposite. Okay, so you don't necessarily have to write down the first one. The third law, you do need to know that if there is a force, there's got to be some other force that's resisting it. Okay? For every action, there is an equal and opposite reaction. Okay. So now I'm going to give you a table full of all of these types of forces we might talk about, we might use. This is just really for you to kind of have as a reference. It kind of tells me what the labels are for each of the different forces. It tells me, just what they might be labeled as. So we've talked about a few of these so far. We've talked about friction. We've talked about the normal force. And we've talked about the weight force, right? Those are three that we should be familiar with and the way they're labeled. Fg, Fn, Ff, right? A couple others here, spring forces. It's just the force that it would take to stretch a spring or compress a spring or put it back to its regular equilibrium. The tension force, that's something that we are going to be paying attention to. So maybe just take a look at that. Tension is anytime we have a force exerted on a string, rope, or cable. So whenever we're pulling something with a rope or something's hanging from a string, it's got a tension force, right? It's not resting on a surface. It's got some sort of tension on it, okay? So that might look like, you have like a bucket that's held by a string. So my free body diagram might look something like this, right? Here's my tension force. Here's my gravitational force, right? That's all that means. And you could still even call it something else, but usually when we have a rope or a cable or a string or something like that, we're going to call that a tension force. Thrust force, we really never use that. I wouldn't add too much with that. Something I maybe would add is F applied. I don't know, maybe just put it off to the side here so we don't forget it. That's just anytime we apply a push or pull, we're most of the time going to label it as F-A-P-P, F applied. Okay? So the last thing we're going to kind of focus in on today is the normal force. We talked about it a little bit last time. The normal force is a contact force exerted by a surface on an object, right? We said that in order for something to have a normal force, it has to be sitting on a surface. Any surface, the road, a table, whatever it is, right? It can be a surface. And so that's what we're going to look at today is the last little section here is a normal force. Okay. When we talk about, When we talk about normal force, we need to understand, first and foremost, it's most of the time a vertical force, right? Because if something is sitting on a surface, the surface is exerting a force upward. We need to know, this is kind of just a reminder, we've already talked about this, but the net force on any object that remains at rest is 0. Okay, so if my object is not moving, the net force is 0. Okay, so I want you to think about this. If I'm moving my calculator, sliding my calculator along the table, it's moving, right? But is it moving in the vertical direction or the horizontal direction? It's moving only in the horizontal direction, which means my net force in the vertical direction is what? 0, right? My object, my calculator, as I'm sliding it across the table, is only moving in the horizontal direction, which means my vertical net force would be 0, okay? And when I'm focusing on the normal force, that means I'm looking at vertical forces. Okay. Let's take a look at this example here. And I'm going to kind of redraw these forces because I don't love the way they have them drawn. But I want to look at the 3 scenarios here. And we're going to actually solve for the normal force in each of these scenarios. Okay? let's say for this first one, here's my object. I've got a gravitational force, and I have a normal force. Can you guys see that? Okay. Okay, so on the first object, I want to calculate the normal force in all of these, right? For all of these scenarios, I'm going to solve for Fn. Okay, and I'm going to say that my box has a mass of 10 kilograms. Okay, in all of them, I have a mass of 10 kilograms. So let's focus just on the first scenario first. I've got a gravitational force, and I've got a normal force. Otherwise, there's nothing acting on my box, right? Literally nothing. So what's my net force going to have to be? My net vertical force, what is it? It's 0, right? But before you even really need to get to that, I want you to go ahead and write out your net force equation. F net equals positive forces minus negative forces. So which forces do I have that are moving in the positive direction? Fn or Fg? Fn is my normal force, Fg is my gravitational force, and it's going in the downward direction. Okay, so even though the scenario might be simple, I want you to get used to setting up this net force equation. Okay? F net equals positive forces, Fn, minus negative forces, which was Fg. Agreed? Okay, so now I go and plug in the information I know. I know that my F net is equal to 0 because my object's not moving in the vertical direction. Fn is what I'm solving for, and then how can I solve for Fg? I know that it's mass times 9.8. Right? Fg is mass times 9.8. So I just go ahead and plug that in there, which means that I'm going to have 0 equals Fn minus 98. And so I'll add that to the other side, and I'll say that Fn equals 98 newtons. Okay? When these objects are congruent, when these forces are congruent, you don't have to go through that whole process, but I want you to see how we got there. Okay? When it's not moving vertically and there's no other force acting on it, gravity and normal force have to be equal. Okay? But in the second scenario, that's not the only thing acting on it. Okay? You see what's happening is they're attempting to lift it up with a force of 40 newtons, but it has not left the table. Which means what happens is they're trying to lift it, but they can't. Right? So here I'm lifting upward on this table, but I'm not getting it off the ground, which means all I'm doing is like taking some pressure off the normal force. Does that make sense? If I were to lift up, then my normal force is going to be smaller. If I were to push down, my normal force is going to be bigger because it's going to have to exert a greater equal and opposite force. Okay? So let's go ahead and solve this one. If I draw my free body diagram for the second one, I don't like how they have theirs drawn. I would have Fg. I would have Fn, and then I've also got this upward applied force, which I just like to call applied. You could call it pull if you wanted to, whatever you want. But I've got basically 3 forces acting now. So if I go set up my net force equation, I would say F net equals, what are my positive forces? Right? Fn and F applied. So Fn plus F applied minus Fg. Okay. Now we can go start plugging in the numbers. So is my object accelerating in the vertical direction? No, because it's at rest. It's just sitting there. So my F net is 0. Normal is what I'm solving for. Applied is 40 newtons. And Fg is still 10 times 9.8, right? So still 98. So now I'm going to do this math, combine my terms here. 40 minus 98, what, negative 58? Okay, so that gives me Fn minus 58 equals 0, which means my normal force is 58 newtons. Right? Do you see how it's less than in our first scenario? Because I was lifting up. I'm taking some of the pressure off of that normal force. All right, in the last one here, we're pushing downward on our object. with a force of 40 newtons. So I'm going to redraw the picture here. FG is pushing downward. F applied is going downward, and the normal force is upward. So as I set up my net force equation, I would say F net equals F, the normal force. And then what do? Minus F applied minus FG. Okay. So now I'll go 0 net force equals Fn minus 40 minus 98, which means in this case, my normal force equals 138 newtons. Okay, so when I push down on my object, that surface is having to work harder. Okay, and so it's a greater amount of force. This is kind of putting all the stuff we know together. Okay, if I'm raising a 5 kilogram bucket and the rope I'm raising it with can withstand 50 newtons of tension, what is the maximum acceleration in which I can raise the bucket? All right, so what this is saying is that, do any of you guys go fishing? No? Okay. If I'm trying to raise something on a rope and I raise it too fast, I yank it too fast, there's a chance that rope would snap, right? If I raise it at the right rate, if I raise it slow enough, that rope can withstand. So what we're trying to find here is how fast can we raise it up without that rope snapping? That's really all that we're looking at here, okay? But first things first is that we have to draw our free body diagram. Remember, I don't really care to draw the whole picture of what it is, but if I'm raising up this object, I have to have gravity. And then it says I'm raising it with a rope. So what kind of force do we have if we have any rope or cable? Tension, right? It's a T, tension force. Okay, and I don't know a whole lot about the scale of those vectors, so I don't need to be super concerned about it. But what I do know is that they're not equal, because this object is accelerating upward, right? Because that's what I want to solve for, is what upward acceleration. So I know they're not equal, so I don't have to draw them super to scale, but once we have our free body diagram drawn, then we can start looking at what our net force equation is going to be. Positives minus negatives. So my positive force is tension, my negative force is gravity. Agreed? Okay, when we're solving these problems, this is really our first step. Free body diagram, then our net force equation, and then we can start looking for numbers. Okay? So it says my rope can withstand 50 newtons of tension. So I want to know, if I have 50 newtons of tension in my rope, how fast can I accelerate? So I'm going to plug in 50 for tension. How else can I solve for FG? Mass times gravity, right? So 5 times 9.8. And that would give me F net. But am I really solving for F net? I'm solving for acceleration. So what can I substitute here to get me to find acceleration? What's our other way to solve for F net? MA. So if this is equal to F net and this is equal to F net, can't we just make them equal to each other? Yes. So since I know that F net is equal to mass times acceleration, I'm going to substitute that in right there. Mass times acceleration equals tension minus gravity. Okay? And we actually know that our mass is 5, so I'm going to go ahead and plug that in times A. Okay? So let's go ahead and solve. So this is 50 minus 49 equals 5 times A. That gives me 1 equals 5A. So divide by 5 equals 0.2 meters per second squared.